My name is Magued Al-aghbary, together with my colleague Dr. Mohammed Sobh, who is over there, and Professor Christian Gerhard. We would like to present to you a heat model of Africa using geothermal heat model of Africa using random forest. Let's start by motivation. Why Africa? A large continent, largely unexplored, and there are a lot of things interesting that could be explored there. And in our study, we are trying to overcome the following challenges. At the first place, do we have data? Most of the measurements done in Africa or third world countries are done by national institutes, and those data are treated as a national interest or a matter of security. So they are not publicly distributed. That's one thing. The other thing, if we have data, where are they? If you have data, where are they? How they are distributed? You can see that the data we have are clustered, and most of the data are, the data inside Africa is almost empty. The third question comes, what is the quality of our data? By quality, I am referring to what is the uncertainty in the measurements. In the data set that I'm using of Lucaso, the data set are classified with what they call the uncertainty of less than 10, 20, 30, and 40 milliwatt by square meter. Let's come back to the original question. From what we have, how can we model the geothermal heat of Africa? We can go either by doing interpolation, like kriging, or using one observable, like Curie depth, Curie temperature depth, or seismic velocity in order to get the geothermal heat flow. Or we could use several proxies or several observables. Formally known as multivariate analysis and commonly known as machine learning. That's what I am trying to present you. Machine learning. So if we'd like to do it, we start by collecting the data. We have already agreed that we are trying to model the geothermal heat, so that's our labeled data. And in order to train the model, we can go crazy. We can choose whatever observables that we would like. In our model, we used 16 observables, starting with the MOHO and LAB depth, seismic velocity, S and P wave, as well as Curie temperature depth. Should I point to it too? No. Okay. Geomagnetic anomaly, elevation, densities like lithospheric and crustal average densities, gravity anomalies like free air, geoid, Bouguer and shape index curvature, tectonic regionalization, and global lithological map. Finally, distance to the nearest volcanoes. That is the what. And the second question comes, where we can get those data. We have tried as best as we can to use regional models instead of global models, and try to use the most acceptable and widely recent data sets. I have already mentioned that we have those data on Africa. However, we didn't use all of those data. We constrained or limited our input data to only those, less than 20 milliwatt per meter square. Why? Because simply garbage in, garbage out. If we allow more uncertainties in our model, we will not be that confident of our final model. We also eliminated values that are higher than 200 milliwatt per meter square, because mostly they are attributed to local phenomena that is out of scope of our study, and we are more interested in the global background model. The second thing, after getting the data, we have to pre-process it, because in its current state, it's not of that useful to us. We removed anomalous data, known as well as outliers, so that they don't disturb our model. Then comes the choice of algorithm. I have already mentioned that our data is labeled. It means in the machine learning lingo is supervised data. And beneath this category, we can do several things with this data, like regression, classification, and so forth. In our case, we use regression. Of course, we can do some sort of classification, but it's out of scope of our study. To name few, those are some of the algorithms that can be used with regression. In our case, we used random forest regression. Random forest regression. It's a forest. In the forest, we need trees, and the basic building blocks of the random forest is CART, classification and regression trees. And it's an ensemble technique. It means that it will use several predictors, what they call it weak predictors, and will try to transform them to strong predictor by averaging the outcome of those predictors. And the word random comes from the fact that each tree will be fed with random data, either random features and random records. However, in order to build this model, before that, we need to set hyperparameters. And in order to set that, we use a Bayesian optimization. I am referring to how many trees in this forest, what are the depth of those trees, and so forth. And this process is very important, because if we ignore it, our model can easily be overfitted. Let me just reiterate what I'm trying to do. From the location of the geothermal points measurements, I'm trying to exploit or train the model with the data that beneath them, with my 16 observables. And after building the model, when we present the model, the other observables where there is no geothermal heat flow, it will predict it. I have already mentioned that we use 16 geo-observables. However, are those geo-observables are those geo-observables equally important? There is an internal mechanism in random forest ranks those observables, how they contribute to the final, what they call it, value. And as you can see, there are some observables that they are more important than the others. And this ranking is based on how those observables correlate to each other and correlates to geothermal heat flow measurements. And we found our sweet spot by reducing it to 11. And what I'm presenting to you is the model based on those 11 geo-observables. This is the model that we have built. Let's analyze it. I will overlay the heat flow measurements that used to train the data. As you can see, if you cannot differentiate that much the points that I have put, that's a good sign. It means that the model managed to predict those points correctly. Those are the residual of those points. As you can see, it's mostly whitish, also another good sign. And if you would like to overlay the points that has less than 20 milliwatt per meter square, you can see again the trends is kept. and that is also a good sign. However, we have more residual, and that's normal because the training data itself, they had higher uncertainties. And for the data that are higher than 20 milliwatt, that has a variation of more than 20 milliwatt per meter square, again, it managed to capture the trend. If we would like to overlay the position of the volcanoes, you can see that it managed again overall to capture where the heat flows are. As for the cold parts, those are the West African cratons, Congo cratons, and the Kalahari cratons. And again, the model managed to describe those things, those cratons well. Now, how can we evaluate those values? Now, in your left, you will find the scatter points of the observed value to the prediction, and the error or the normalized root mean square, it's 0.23. The R square is 0.75, and overall our model overestimate the values except for the lower part. It's also evident from the subplot B, where it shows that our values overestimates what they called it, the overall predictions. The uncertainty. We have to use this term cautiously with inverted commas because we are referring to the uncertainties with the predictions, not the measurements. Here, this is the map of coefficient of variations, and it shows us when the value is high that the predictions manage to deviate from the average. And that's quite normal when we have data. When we don't have the data, it means that our model managed to predict, not only interpolate. You can see that in the central part, our model managed to predict, not only interpolate. As for the uncertainty, it's hard to quantify uncertainty with machine learning techniques. However, there is some sort of indirect way, again in inverted commas. We built several models with 4, 5, 6, up to 16 observables, and out of those we try to see where they agree. And you can see that when the values are higher, it means that the models, they don't agree, and we have some sort of uncertainty. And those are the training data again. As a summary, we have started with getting the data, pre-processing the data, building the model, and testing it, and finally getting our final geothermal heat model of Africa. Our recommendation, how we can go further, we have used random forest, which is a classical technique in the machine learning library, and it would be, the second steps would be good to use some sort of neural networks because those techniques are able to fill the gap of missing data. Thank you so much.